Hi, welcome back to Mrs. O'Graham's Maths channel, and we are on to part 2 of the P3 paper for 2019. We're up to question 7. So this one is our vectors question, and it's a fairly straightforward one to begin with. We've got a nice easy one to start us off at 2 marks here with telling us that we've got a plane M that's got this equation here, and the n is parallel to M, which means that it will have the same starting part of its equation just here. So we can get that straight off of that equation. What will be different is the D part. Okay, so it will have the same normal, and then we know that the point P has those coordinates and it's on that plane, so therefore it will satisfy those parts of the equation for x, y, and z. Whatever they come out to be, that will be our D number, so then we put it into the equation of n. Then we move on to some slightly trickier stuff. So we've got to calculate the perpendicular distance between M and N. So we've got these two planes here. How I've thought about this, and there's probably multiple ways to go around this, as there always is with vector questions, is that we've got this plane where P is on N. We were told that in the first question. So we know a point on N, and we know if we go straight up, I'm going to say up, although it might not actually be upwards, but you know what I mean. So perpendicular from N, if we go straight in a perpendicular direction from N to, then we will get to a point that is on M, because that is also having the same perpendicular to this same normal here as 1, 4, minus 8. Okay, so thinking about that, if I put this as lambda being some multiples of the normal, then we can rearrange that to sort of put the OP and that bit together. We know that this position vector here will be on M. So then if we put that into the equation of the plane for M, then we can follow that through and work out that lambda is minus 1/3 in that case. Now, since we're just looking for length, we can forget about the minus portion of that. We're just trying to find the distance of it. So the length between them will be 1/3 of the normal, because of what we set up here, where we know if we start there, we go in the direction of the normal, and lambda is just telling us how far along in that direction we need to go to hit the plane. So 1/3 of the normal vector away, so we can work out the distance of the normal vector and times it by 1/3, and that gives us the answer of 3. Then the last part of that question is quite difficult conceptually to actually figure out what's happening. So we've got this line L that lies on the plane, and I've set that up here, passing through a point P. We know it's on the plane N, so we have the equation of N here. Now we also know that the line itself is perpendicular to the position vector OP. If the line is on the plane, it will also be perpendicular to the normal to the plane. So we've got two things that we know it's perpendicular to. Now I've labelled Q as another point on that line just to make it easier to talk about. So we need the direction of this line, which we can call as it being P to Q. We will have the equation of the line being that start point, so the position vector for P, plus multiples in the direction of PQ. Now if we know that PQ and PQ is perpendicular to both OP and the normal, then we can use the vector product to work out the direction of PQ. So if OP and the normal, if we put them together into vector product, we will find a vector that's commonly perpendicular to both of them. So that will be PQ. So our vector product equation is down here, which gives us the direction of PQ, which I've just halved all of those numbers to make it simpler in the equation of our line. Question 8 starts off with a nice easy 3 marks for a trapezium rule. So as long as you know how to use a trapezium rule correctly, then you can get down to 1.85 as an estimate for the integral there. Then we need to say whether that estimate is going to give an overestimate or an underestimate. So this is done with a diagram. Now we've got a concave curve here, so if we drew trapezia underneath that, then those trapeziums would be bigger than what the curve would have given us for the area under the curve. So therefore our estimate in part 1 is an overestimate. Then we have part 3, and for this one we need to work out where on the curve we get a gradient equal to 2. So differentiate that first, and that's just using the chain rule. Set it equal to 2, and then we've got an equation to solve. A little tricky because it doesn't factorize, but you can use quadratic formula on there or completing the square to get down to x equals 0.896. Then we've got question 9, which combined both partial fractions and differential equations into the same question, which was asking a bit much really, but you should be able to know both of those. Once you actually knew what you were doing, the maths of it wasn't too hard. Okay, so first of all, if we put those, sort of forget about the dx dt for a second, but just turn the 5 and the right hand side into partial fractions. So I've taken the right hand side over to the left to make it 5 over those two brackets, separate those into partial fractions, and then we get this part down here. So then if we want to, we need to separate the variables, so we have dx on one side and dt on the other. So bring the dt up to the right hand side. We have the partial fractions that we just worked out from this top bit up here, and then we integrate both sides here. So the integrals, you can follow them through my working through those ones, and we need to use logs to integrate this because we've got 1 over something with just a singular x down there, and then using log laws to rearrange that. We then substitute in the information we were given, which is that when x is 10, t is 0, to work out what c is. From that point, it's about rearranging. So we get down to this bit. We can continue that down so that we get x equals this part here. Now it'll be interesting to see on the mark scheme just how far through that you needed to go and how much simplifying was needed. I would assume that if you got down to something equivalent, you'd be given the answer, given the mark for your answer. Part 2 wants to know what happens to x as t becomes large. So if you just go back up to this, if we made t very, very big, then this here would get huge, this would get huge. The 40 and the 1 will become insignificant. So, and these two things obviously are the same. So whatever that very large number, they would sort of cancel out. 40 and 1 would make very little difference to a very big number. So we would end up with those cancelling down to 1, and the 60 divided by 3 would cancel down to 20. So x would approach 20 as t gets very big. Which brings us to the final question, question 10, which I thought wasn't too bad, as long as you were very careful about what you were doing as you worked through it. So first of all, we need the x-coordinate of m, which means we need to differentiate, set it equal to 0, and carry on. So we've got, I've just separated those parts for the product rule down here. That gives us the gradient. Then if we set that equal to 0, we can work through this here. So we've got that, first of all, if we factorize out that e to the cos x, e to the power of anything can't be equal to 0, so we carry on with this bit in the brackets equals to 0, take out a factor of sine squared x, and then we know that sine squared x equals 0 doesn't give us the answer that we want. It wouldn't give us the value of m. It gives us 0 and pi, which is where it gets back down to the axis again. So then we want to carry on with this part of the equation equal to 0 and solve that. So we end up with x being 1.26. And we finish the paper with a question that requires us to do integration with both substitution and later on you'll see by parts as well. So this one had room to make lots of errors and you had to very carefully work through it. Okay, so first of all, use the substitution u is cos x. So over here I've just done my little breakdown of the derivative to get what dx would be equivalent to. So then we can replace cos x anywhere in here with u. So e to the cos x becomes e to the u. If we replace dx with its equivalent in du, we get this. So we get the sine squares cancel down to minus sine squared x. Now sine squared x is the same as 1 minus cos squared, which we can call 1 minus u squared. So we put that into here. Now since it was minus sine squared, it becomes u squared minus 1 instead of 1 minus u squared. So continuing on with that, and you can see my little scribbles down here on the right hand side. This is not good mathematical notation, but this was just how I could keep track of the next part where we do integration by parts a couple of times. So this bit here, I've done an integration by parts using that the dv by dx part that's in the formula I called EU, because that's the easiest thing to integrate, because it just goes to e to the u. And then the u part of the formula, although that's why this notation isn't great, because we're using u, but I'm just trying to refer it to what's on your formula sheet. So u squared minus 1, we differentiate that, it becomes 2u. So then we go over to this bit here, which is, this is the result of integrating by parts. So this is minus the integral of the v du part. So if we integrate e to the u, we get e to the u. If we differentiate u squared minus 1, we get 2u, and then we have to integrate that. So now, next line, we have this part here is the 2u multiplied by the integral of e to the u, which is just e to the u, minus the integral of the derivative of 2u, which is 2, times the integral of e to the u, which is e to the u. So we've done differentiation by parts again. So then we've got this final step here. We're finally down to a bit we can just straight off integrate into 2e to the u. So then our area becomes the definite integral of this thing between the limits of 1 and minus 1. Now notice that those limits are not the same as we started with up here. I didn't talk about that yet. So here we've got 0 and pi. If we change that into the values of u is cos x. So cos of 0 is 1, so that becomes a 1 at the bottom, and cos of pi gives us u is equal to minus 1. So that's why we've got these limits down here at 1 and minus 1. And then if we put those in as the definite integral, we'll get our final answer of 1.472. And that really was a wow question. Well done if you got that and didn't make any mistakes along the way. And that's it for the P3 paper. If you were sitting that one, I hope you did well and you're not in tears at the end of this video. If you're looking at this preparing for your exams coming up, then good luck. If you found that helpful, then do me a favor and click on that subscribe button and like the video so that other people can find this and find it useful as well. Thanks a lot.